Chapter 2, Standards for Measurements. Measurements are key in all of scientific endeavors. And basically what makes up a measurement is you have both a number and a unit, which expresses a value of something. We're going to run into scientific notation. Scientific notation is a way to write really big numbers, or to write really small numbers. For example, let's draw a number. 0.0 0 0 0 0 0 0 0 0 0 7. Writing this number 5 times, it'd be easy to make a mistake. Let's put the dot in thicker there so you can see it. If we wrote this number, you're at a risk of actually putting in an extra 0 or forgetting a 0. And if you did put in an extra 0 or forget a 0, you would change the value of the number 10 times. So really big numbers, we could also make up a gigantic number. 8 0 0 0 0 0 0 0 0 0 0 0 0 0 0. If you had to write that multiple times, it's easy to actually get an extra 0 or miss a 0. And so scientific notation is a way to write very large numbers and very small numbers in a compact form. And the formula for scientific notation, let's erase our number, is we first have one digit, and it has to be 1 through 9, it cannot be 0. So a non-zero number dot the rest of our sig figs times 10 to a power. So you'll always have a non-zero number, then a decimal, then the rest of the significant digits, which we'll get into what a sig fig is in a little bit, times 10 to a power. Now a quick way to know whether your exponent should be positive or negative is if your initial number is bigger than 1, you will have a positive exponent. If your initial number is less than 1, you will have a negative exponent. So here, 0.000423 in scientific notation. This number is less than 1, so we're going to expect a negative exponent. And this decimal point will move 1, 2, 3, 4. It's going to move 4 places to the right. So we're going to end up with 4.23 times 10 to the negative 4. And again, if you're not sure if it should be negative 4 or positive 4, ask yourself, is the number bigger than 1 or smaller than 1? This number is smaller than 1, so we know it's going to be a negative exponent. If a number is bigger than 1, let's say we have 5,000. Nice easy number. On this one, the decimal point moves to the left because it would be here. So it goes 1, 2, 3. So it'd be 5 times 10 to the third. So notice when they say if the decimal moves to the right, you have a negative exponent because up here it was moving to the right. If the decimal moves to the left, it'll be a positive exponent. And again, an easy way to double check that is to ask yourself, is the number bigger than 1 or smaller than 1? If the number is bigger than 1, positive exponent. If the number is less than 1, negative exponent. So this one, 353,000 to 3 sig figs. That'll be 3.53. And then our decimal point is going to move to the left because it would be here. 1, 2, 3, 4, 5. 3.53 times 10 to the 5. Double check. Positive exponent. Is that number bigger than 1? Yes, it is. Measurement and uncertainty. There are 2 types of measurements. You can count something out or you can use a tool to measure something. If you count something, it should be perfectly accurate. If I give you 3 eggs, you should know that you have 3 eggs. If I give you 7 eggs, you should know exactly that you have 7 eggs. Uncertainty comes in with measurement. If I give you a tool and you have to measure something with a tool, you are now limited by the tool itself. When we have a measurement, we will have a numerical value and a unit of measurement. You must have both a number and a unit. If I say I live 5 from here, that doesn't mean anything. But if I say I live 5 miles from here, now you have an understanding of what I'm saying. So all measurements must be expressed with both a numerical value and a unit of measurement. Both are needed. Here we have a thermometer, and we see the temperature is above 21 and it's below 22. Of that I'm certain of. What I'm not totally sure of is exactly where it is, and this is the problem with measuring with a tool. Inevitably, whatever you're measuring ends up in between your two last calibration markers, and you have to estimate. So when you use a tool, your last digit is always an estimation. Now you could look at that and say that's 21.1, you could say it's 21.2, you could say it's 21.3, they would all be correct. Because in a measurement, the last digit is a guess. And people guess differently, and thus there's uncertainty into the measurement. If you take more complicated classes in engineering, they'll go over how to really deal with uncertainty. This class we use a really simplified version. Basically all measured numbers are plus or minus 1 of the last digit. And that's the hardest part of this chapter, is that most students come into this chapter thinking a number is a definite point, when in reality with a measurement, a number is a range. There's always a plus or minus to every measurement. So again, numerical values obtained from measurements are never exact values. There's always a plus and minus to them. So some degree of uncertainty exists in all measurements. The very last digit of a measurement is guessed, is definitely estimated, and thus there is uncertainty. Because of this level of uncertainty, any measurement is expressed by a limited number of digits, and these we call the significant digits, the ones that are important. So here again we have our thermometer. Notice I got a better thermometer. Now instead of having a dash every degree Celsius, I have 10 dashes every degree Celsius. Whereas before I had to guess at the 10th of a centigrade, now I'm guessing at 100th of a Celsius. Again, when you look at a measurement, you'll always know what tool took the measurement, because you always report your answer one digit past your calibration markers. So here, on the left here, this thermometer has a dash every degree Celsius, which means we report to a 1/10 of a degree. Here, I have a dash every 1/10 of a degree Celsius. Therefore, I report to the 100th. If I gave you a thermometer that had a dash every 100th of a degree, you report to the 1000th. If I gave you a thermometer that had a dash every 1000th of a degree, you'd report to the 10,000th. You always report a measured number one digit past your calibration markers. And that last digit is an estimation, because it ends up falling in between two calibration markers. On the odd chance that it's right at a calibration marker, you can put a 0 at the end. But that's important, because 22 is a different number than 22.0. When I say 22, what I mean is bigger than 21, smaller than 23. When I say 22.0, what I mean is bigger than 21.9, smaller than 22.1. And so the allowable slop in the number is much less. It is a much more precise number. And so terminal zeros matter. And here are the rules for significant figures. All non-zero digits are always significant. 1, 2, 3, 4, 5, 6, 7, 8, and 9, always significant. And defined numbers are always infinitely significant. For example, there are 12 inches in a foot. Why? Because we say so. That's why. It's a defined number. Defined and exact numbers have no uncertainty whatsoever because they were defined that way. So the only hard part is with zeros. Sometimes they are significant, sometimes they are not significant. If they are sandwiched in between non-zero digits, they are significant. And so this 0 right here is significant because on both sides it has non-significant or non-zero numbers. But it doesn't have to be directly sandwiched. So I can give you the number 80,008. 8, 0, 0, 0, 8. All three of those zeros qualify for the sandwich rule because somewhere on both sides of them there's a non-zero number. So again, the non-zero numbers don't have to be directly adjacent to the zero. They don't have to be touching the zero. Just as long as somewhere on both sides of the zero there are non-zero numbers, it is a significant zero. And we call this the sandwich rule. They are sandwiched in between two non-zero numbers. Zeros are significant where they're at the end of a number with a decimal point. Like we said, 32.410 is a different number than 32.41. That last zero does not change the value of the number, but it does change the uncertainty. It changes the precision. It changes the plus or minus in the number, and therefore it's important. Zeros are not significant only when they're acting as a placeholder. For example, there is no other way to write 0.00321 without those zeros. Those zeros are placeholders, and they're filling up the tenths and the hundredths so that we can put the 3 in the thousandths place. And so they are not changing the value, they're not changing the uncertainty. Really, it's just a limitation of our number systems is that they're needed as a placeholder. But in scientific notation, they disappear. In scientific notation, 0.00321 becomes 3.21 times 10 to the negative third. Those initial zeros disappear because they're not needed. They don't signify anything. If a zero ends up at the end of a number with no decimal point, and that is absolutely essential here, because if there is a decimal point, it's significant. But if there's no decimal point, it's not significant, because again, it's a placeholder. There's no way to write 6,920 without that zero in the ones place. It's a placeholder, and so we have to put it there. So let's practice. 3.2 inches. How many sig figs? 2. 25.0 grams. That 0 is at the end of a number with a decimal point, so 3 sig figs. 103 people. This is a trick question because you don't measure people, you count people, and a counted number is an exact number. You expect counting to be done correctly, and therefore it should be infinitely significant. 0.003 kilometers, 1 sig fig, because the other zeros are placeholders. And again, let's say we change the units to meters. This would be 3 meters. Notice when we change units, those zeros disappear. If this had been 0.0030 kilometers, then it would be 3.0 meters. Significant zeros stay when you go into scientific notation or change units. Not significant zeros disappear when you change units or go into scientific notation. And that is the end of part 1 of chapter 2.